Okay, I think we're back. I think we are actually functional now. So, Brian. Oh, okay. So, wait just a moment and we will get started with this talk, but I at least got the technical side working now. Yes. There will be some successes in this world. Awesome. Okay. Floor is yours.
Right.
If you want to just talk, here, from here, you can just, I think it's down. Hold on.
Oh.
Hold on. I had this. I had this. I really did. It is left and right.
All right.
Excellent. Okay. Yep. All right. All right. Let's get started.
All right. So you should recognize the background of this slide from Brett's talk. This is just Caves of Cud's internal Dijkstra Maps visualization. I'm going to talk about the artificial intelligence in Caves of Cud and Sproggiwood. So I'm Brian Bucklew. I do the programming and production at Freehold Games with Jason. This is, I'm going to say, part 2 of a talk series. The part 1, I talked about the entity component framework. I'm not going to cover that, but if you missed part 1, you shouldn't be too lost. The target of this talk is not to push any kind of boundaries. So I'm not going to technically impress anybody that's written and shipped a roguelike, but instead what I want to do is try to short circuit some of the difficulties you have coming into a roguelike. I find that people in a roguelike development, because they look at it and they say, this seems like something I could do all by myself and it has no graphics, so it should be super easy. And in fact, it's one of the most difficult things you can possibly do in video game programming. And you run into many roadblocks. One is just structuring the engine. And so if you're having problems just structuring your engine at all, part 1 covers how I at least solved it in Caves of Cud. What I'm going to talk about too is when you realize that, oh geez, roguelikes have these very flexible creatures that can do all kinds of things, and now I have to write an AI that does this in some kind of way that doesn't explode dramatically. So here's my titular quote. So Minsky says, we'll show you that you can build a mind from many little parts, each mindless by itself. And I actually think this is a good principle in general for building software. But you look at something and it is extremely complex and the results are chaotic and just unfathomable. And what you want to do is try to break it down to the point where it's composed of little entities that are pretty deterministic and understandable, right? Give those guys an interface and figure out what they're going to do. And let's talk first about our requirements, like good engineers. The first 2 are really the core requirements of Caves of Cud. We want a big emergent sandbox that feels credible. This is, for most roguelikes, the kind of core requirement. The second one that I like, because I'm a lazy guy and I don't like to remember a lot of stuff, is that I generally want to keep my source code out of the way of my inspiration for game development. So I don't want to have to remember all the cool stuff that I did to make it work. I want to get that complexity, box it up, and then be able to work on a new feature without that adding complexity exponentially. So when I go and add a 50th kind of monster, I don't want to have to remember what the other 49 kind of monsters did, even a little bit, in order to add that 50th kind of monster. The following 3 requirements are more specific to Caves of Cud in general. We wanted to be able to take any creature in the game and mutate it dynamically. So you want to be able to take the player or a goat and let it shoot fire or fly. We want to be able to copy any player. We had some very specific ideas in mind for abilities. So you want to be able to take the player and let him create 10 clones of himself and have these clones fight for the player in a way that feels credible. And we want to, in general, provide a means to let very strange creatures do very strange things. So that if you have like a giant chrome pyramid surrounded by a force field, that it behaves credibly as a giant chrome pyramid. And this is obviously very different than like a little hyena man or a big ball of slime or the player with wings. And so this poses some real challenges to an AI system that has to adapt dynamically, because you can combine these things. So the player can run into a giant chrome pyramid, take over his body, mutate to add flame jets, and then copy himself. And these copies should behave in a way that is not perfect, it at least feels credible. And so this is sort of, I said I would talk about Sproggiwood and Caves of Cud AI. So the complexity explosion anti-pattern, which is what my AI looked like for the first few years of developing roguelikes, is actually what Sproggiwood's looks like, because the requirements for Sproggiwood were much better constrained. We didn't have extra designers. The design was very tight. We had very few monsters, and we wanted them to behave in a very deterministic pattern. When you take this pattern of making very specific checks, like say, if my hit point is less than 30% and my inventory contains a healing item, use a healing item, and you start building this out in a way that handles something with the complexity of Caves of Cud, you find that you end up with about 20 million lines of this code. And if you add a new ability, one, you have to figure out where you want to insert it, so your complexity is growing exponentially. And the second is that you introduce coupling between whatever component is running the AI. And so you can imagine this being the function that runs when a turn is executed. So that when I add, say, a healing potion, I've created the healing potion. There's a piece of code somewhere that's healing the player when you drink it and popping up a message. And then somewhere else, I've got to go hunt up the brain code and wire it in to the healing potion. And so this coupling is another thing that increases the complexity of the system. And so this is fine for low complexity systems, but it grows exponentially, and so that's pretty bad. So we're going to take a look at the core solution, and then I'm going to show you it in action, and then we're going to look at it again. So this is essentially all of the code of Caves of Cud's AI behavioral system. So if you've watched part one of the talk, or you've used Unity or any other component entity framework, the brain is a component that sits on an object. It has a stack of goals. And when an actor takes an action, first, this line of code takes all the goals that have finished and gets rid of them. And this is important because, say you've got a goal of murdering something and something else killed it during the last turn, your goal is finished, right? You're like, I'm done murdering this guy. I can go back to whatever I was doing before. And then what it does is it takes the next action. So if you look at the definition of a goal, so this is a base class. I implement specializations of this, like murder someone. So the goal can be finished or not. So the goal of murdering someone is finished when your target is dead. It has an implementation which knows roughly how to murder someone, and it has an original intent. So this is useful because, as I'll show you, the goals tend to fracture into smaller goals that may fail. And so what happens is that those goals, when I try to move towards the player and that fails, it says, well, let's just go back to my original intent, and it will plan another set of goals to murder someone. So let's look at a simple example. So everybody uses G's because they're goblins, but in Caves of Cud, they're snapjaw hyena men. So we're going to look here on the right at a goal stack for a snapjaw in Caves of Cud. So right now it's got one goal in its stack to kill the player. So this is an implementation of that goal class. And it's not finished yet because the player is still alive. So on its turn, it's not popped off, and it says take your action. So the kill the player class has a little planner. It says, well, I'm not close enough to it. And I'm going to go into detail into kill the player since it's a very important thing in roguelikes is murdering stuff. But let's say it's determined that it needs to approach the player because it can't do anything at range. So it pushes an approach the player goal onto the stack. So that gets a lot of the complexity already out of killing the player. Killing the player says, I just want to approach the player. So approach the player is a very constrained class that is able to use movement mutations and stuff in order to get closer, but kill the player doesn't care. And so approach the player in this class will run an A-star algorithm, and that results in 4 more mini goals. And these are very constrained. They're not going to have to push any more goals. They know to move east, it's going to move the token east. And so on its next turn, move east will execute. And so now it's moved 1 east. The stack, that guy's popped off because he's finished. So we're going to move east again. And now the player has created a wall. So on the next turn, move east is going to execute. At this point, I'm not A-starring anymore because it's not really efficient. But if anything fails, in this case it will say, I can't move east, there's a wall there. It will say, well, let's go back to our original intent because whatever the stack of goals that we've stacked up are not valid anymore. So we fail back to approach the player. Approach the player is going to run again saying, oh, well, I needed to move to the player. It's going to run an A-star, push a bunch of little move goals back on the stack. And so we're back here. This is what the core AI game system looks like. Any like questions about that so far?
What if the player moves? You recalculate it?
So the question is, what if the player moves? There's a little more complexity in the system, right? You can engineer this in a bunch of ways, right? You can run A-star every turn and just push a single move onto the stack, for instance, and Caves of Cud will actually do that. Sometimes it does that dynamically based on how much load there already is in the system. So I can decide whether I want to push 8 of them on the stack. The other thing I can do is push more of them onto the stack if it's out of sight. So it doesn't really matter if it looks dumb, right? And so in close action, what's happening is approach the player is executing. It's pushing the next step onto the stack. And so it's recalculating in real time most of the time. But the nice part is it's very controllable, right? You can say approach the player in a way that matters if they care or not, or in a way that you're going to recalculate next time. And the implementation is literally how many more goals do you want to push onto the stack there. And so it's very tunable. Any other questions before we go? Okay. So let's take a look at this in action. So we've got a snapjaw on the left there and a player on the right here. And we've got some pizza in the hall between the snapjaw and the player, and a couple webs. So I won't go through A-star. I'll give you some resources to go dig into it. It's a well-solved problem, so and those resources are going to describe it much better than I can. But one of the important things about A-star is that you want to understand what the weight of moving through each cell is. So you don't want to step on pizza because it's very hot and you'll catch on fire, and you would rather not step into webs, but you might if it's very important to move away. And so what I do is I calculate a weight map for a creature. So this is, again, pretty basic, but I thought it would be very useful to people who are just A-starring at first, because the basic idea is, oh, well, I'm just going to path. And what you want to do is, in fact, apply these weights. So if we snap back, you can see the 2 webs there to the right of the snapjaw. They have a little bit of a weight, a 3, and so A-star is going to tend to avoid those. And you can see that the lava there in the hallway and other players have a very high weight, but are not strictly impassable. And this allows very interesting emergent pathing, where if, and say there's 2 snapjaws, one standing in a hall, and there's another way around, A-star will pretend or will prefer to go around and come in behind the player. But if there's only one hallway there, they'll just stack up behind it because they're going to path through that as a means of last resort. And so what you see here is the path that he decides is kind of in between those 2 3s and around to get the player. And so these navigation weight maps have a few interesting things that weren't obvious to me when I started building them. One is that they may be different depending on who's building the map itself. I keep some caches of these weights so they don't have to recalculate this whole weight map every frame. It only really matters if the contents of a cell change. So if you're smart or not, for instance, if you're a dog, doors have very high weight because you cannot open doors. Whereas if you are a smart person, you can open a door as a very low weight. It doesn't really matter. If you're burrowing or not, walls have a different weight. So that if I'm a burrowing creature, walls have a very high weight. You would prefer not to have to dig through a wall to get to a player. But if you are burrowing, then you will do that as a means to get to the player no matter where you are. The other thing, which was also not obvious to me starting out, is that the player has very different auto-pathing mechanics than a monster does. Whereas when I'm autopathing as a monster, I can do things that are kind of goofy. I'm going to end up in a web, or I'm going to step on lava occasionally. If you're autopathing the player, like I've clicked on a square with the mouse and I want to path the player's going to get very mad if you do something that's even a little deleterious, if you end them up in a web. So you have to give all those things essentially infinite weight and force the player to make that move. And so what I do is I have a few bits, whether they're smart, whether they're burrowing, whether it's the player or not. And so each cell has a few weights. In this case, you've got 3 states, so you have 8 possible cell caches, and you can do more than that. It's a byte each, and so it's very memory efficient. The cell values are cleared when the object list changes, so when something enters the cell or leaves the cell, I automatically invalidate the caches. But this means in most frames, I'm only recalculating 6 of the cells or something, because very few contents change. And it's also possible for objects to say, hey, cell, clear, invalidate your caches because I've changed what I'm going to report. And that doesn't happen automatically. The objects have to decide to clear that cache. So this is just for later reference. Blob Games has a super amazing website that goes through all kinds of techniques, not only A-star, but Dijkstra Maps. And I use heavily in my projects the A-star pathfinding project in my Unity projects. It's a super awesome generic A-star implementation in C# that handles generic graphs, not just grids. And so it's very useful for even like 3D spaces. So one immediate question is, if my stack is empty, how do I get that stack going? And so there are many ways to solve this problem. My solution at the time was to make sure that a stack is never really empty. If the stack is empty, I push on a board goal. So the lowest your stack can get is 1 board goal. And here's the full implementation. The first thing that happens is it fires an event on every component in the game object and item that says, I'm about to be bored, is there anything I want to do? And if nothing has a very specific idle action that they'd like to take, it tries to see if it wants to start killing someone. And you can imagine how that's implemented, that you look for someone you want to kill, and then you push a I'm going to kill you onto the stack. And if none of that happens, my board goal has some basic idle activity. They might wander around or whatever they want to do. So this is an example of a component that handles this I am bored event. In Caves of Cud, we have pilgrims that migrate across the continent. And the implementation for these is relatively straightforward. It's if you get an I am bored event, so the stack is empty and they want to figure out something to do. They say, well, I'm always going to, if I'm bored, push a new goal and a pilgrimage goal. And this goal is able to path its way across the map to get to the citadel. If they get interrupted, if something attacks them, combat goals will go on the stack. And then once those combat goals resolve, they'll be back to go on a pilgrimage goal, and they'll just head across the map. So let's talk about the kill something goal. Because even with goal-oriented action planning in this way, you still have a problem of exploding complexity inside individual goals. So it doesn't fully solve the problem. So the kill something goal in Caves of Cud is by far the most complex. And this is the solution we're currently executing on. I don't think this is the best one, but it works very well for Caves of Cud. It's very controllable, and we'll walk through how it works. So if something has a kill something goal, the kill something goal has a target, so I'm going to kill whoever this is, usually the player, but not always. And it's finished if the target is dead. Each turn that the goal executes, we go through a pretty rigid set of attempts. The first thing we'll do is try a melee attack. And if that doesn't work, we're going to try a defensive action. If that doesn't work, we're going to try a ranged action. We're going to try just using other items we have, and then we're going to try a movement action. And if that doesn't work, we're just going to fail back to the intent, which was usually the board goal. And a lot of times that will just push another I'm going to kill you a goal on the stack, and they'll keep trying. But if something else triggered the board goal, like I mind controlled you and I sent you off to attack, that will eventually fail and they'll just wander away. For instance, if they got like trapped in a wall and they can't even move out of it, they'll just go back to whatever their default behavior is. So how do we implement each of these try melee, try defense, try range in a way that isn't explosively complex? So each of these is basically this template. And so what happens is we have a weighted list of possible actions that can be made. So we start with an empty list, and you can imagine this as a bag which people can put balls into. And what's going to happen is we pass that bag around with this fire event to all the components in the object, as well as each item that they have on their body. And we say, give me balls of type defense. You're dealing with this target, and this is who I am, the parent object. And that gets passed around, and then we look in there and see if anybody put a ball in this bag. If we do, we mix them up, pull one out, and take that action. And then we're done with that turn. And so this is what that weighted action list looks like. It's basically just a bunch of entries with weights and a delegate, to some arbitrary delegate that is the action that's going to take. And you can see the implementation here. I won't walk through it, but you can imagine that that's how it works. Sort of a weighted bag of balls. The weight is the number of balls you're throwing in that bag. And so let's look at a specific instance of this. So at the beginning of the talk, we talked about the healing potion. So this is a potion where it's got some code that can inject it into a particular object and heal the player. And you don't want to go to the brain and also have it know about healing objects. So instead, what it does is it responds to this get actions event. This bag of balls has been passed to it, and the salve injector itself, which is a healing potion in Caves of Cud, will say, oh, okay, well, I've got a request for a defense type action bag. I'm going to see if the object I'm working on's hit points is less than 30%. If so, I'm going to add an action with a pretty high weight to inject myself on this object to this bag. And that's it. This is actually in the same component that implements the way the salve injector is rendered and what actions pop up in the menu. And so all of the AI logic that controls a salve injector is carried along with the salve injector itself. So each item that we add has no additional complexity impact on the rest of the game. It's all bundled up in the salve injector. And so we get a very nicely linear increase in complexity when we're adding new items in Caves of Cud, which was really, when you have so much very fine-grained behavior, is really the core requirement. And so this achieves it. There are other ways to do it, but this works well enough that we're able to have thousands of items in Cud, and really it served us really well. Now, you can look at this, and it's also interesting because you can build some pretty complex behavior into here. For instance, this is saying, hey, if hit points is less than 30%, add 100 balls. You could say, hey, well, if it's less than 90%, maybe have only a 50-50 chance of adding a ball to the bag. And you can add relatively complex behavioral logic inside of the items themselves. And the only real downside is that it's not directly tied to the object, but even that is avoidable, because you could ask, hey, is the parent object I'm dealing with, does they have an intelligence above 6, right? If they do, then add a ball to the bag, and if not, don't, because they're not smart enough to use a healing object. And so again, the actual user has no clue about any of this logic. It's all coming bundled with the object. So this is effectively an inversion of control between the AI system and the items themselves. So I wanted to close and talk a little bit about Dijkstra Maps and Caves of Cud. Brett and them have already covered it. You can see this is actually just a couple frames of Caves of Cud's auto-explore Dijkstra Map implementation. And if you want to check out a good implementation, I would say go to Blob Games and check out the Rogue Basin article that Brett and them already covered. And that's it. Any questions?
Is this slide set going to be available somewhere?
Yes, definitely. I will post. Oh, the question is, will the slide set be available anywhere? And yes, I'll post it on my website, and I'm sure Cal will have it up on stuff.
So there was a magic number 100 in that. Is that sort of a non-linear? You have to think about what priorities have already been allocated, where they are. Do you have an auto-tuning step?
Yeah. So the question here is, in my example, I'm using a magic number 100 here. And yeah, that is just an empirically determined number. In Caves of Cud, that number is actually always 1. So I intended fully to have like a really weighted system and they would make interesting actions. It turns out that just adding 1 ball for each action in there turns out pretty well. And so I haven't needed to tune it any more than that. If you wanted a more Caves of Cud tends to be a sprawling kind of world where weird things happen. And so you might have other design goals than that. And in that case, yeah, you would want to find some other way to tune that weighting. But it's definitely not required to just have a fun roguelike. Any other questions?
So I have very similar systems, and I always find that one of the big tensions, especially on like the 3rd, 4th, 5th time writing through some of these things, is when you're data driving stuff, when you choose to subclass in code explicitly for a new item versus when you try to have 6 different data variations on an item, like, and where do you personally draw the line?
Well, okay, so since we just have me and Jason, up until very recently working on the code, I haven't made a strong delineation between externally scripting, making them available, and having it just be in code. And so what I've done mostly is create new classes when the behavior starts to need too much parameterization. And that is a very loose, a loose terminology. But usually, if it's getting beyond 2 or 3 little flags that you're switching from more behavior, I will copy that out into a new behavior. But yeah, I don't have a good solution for that problem. The question was, how do you decide when to subclass this versus just parameterize behavior? And I don't have a good answer to it.
For me, one of the decision points has been for like Boolean switches, then it starts feeling like another behavior crammed in there.
Right.
For fuzzy switches, it's like, well, how much is the hit point threshold for how many balls in the bag? For me, those can be sandwiched into one.
Right, and so Squirrel said the logic point has often been that if you actually have a Boolean toggle, it's saying that you're probably jamming 2 pretty clearly different behaviors in there, whereas other parameters that can be tuned on a more dynamic basis, on a more analog basis, are often just variations of the behavior that are more natural and can stay in a single goal implementation.
Hi, you have a very specific list, very specifically ordered list of trying things, melee, defense, ranged items, movement.
Yes.
Have you found any issues with that order or cases in which you needed 3 items for some items that like being activated on melee or whatever?
There have been 1 or 2 cases where that's true, and what I've done is simply have those items unnaturally respond to a melee event, right? So that an item that might otherwise be a movement event, for instance, we have a jetpack that will let you make a very powerful melee attack against the enemy, and so it will respond actually to both the melee and ranged asks, even though it's like sort of strictly a movement of ability. And I haven't found any situations where that falls apart. You can obviously look at that list and imagine a more dynamic way to choose actions. But I find that this compartmentalizes my thinking, and there's nothing that prevents me from responding anywhere in that sequence. And so it's basically just an arbitrary label on a priority sequence, which is more readable than priority 0 actions, priority 1 actions. And the corner cases that fall out where you're doing a non-melee attack in melee still feel naturally like something you're doing in melee range, and so it ends up working better than you might expect to just name those priority levels. Any other questions?
Not a question, just a comment. Just your way of putting that of, hey, it's a non-melee thing in the melee set, reminds me a lot of like collectible card games like Magic, where you treat this like this part of the turn even when that doesn't happen in some cards. Right. Because screw it.
Right.
The individual card overrides the general action every time.
Right.
So it's almost in that vein.
So Kawa's comment is that picking sort of arbitrary names for phases is also present in games like CCGs, where you're not, things can happen during the begin combat phase that have nothing to do with begin combat, but most of the things do, and it gives a good mental hook to understand when in the sequence these things are happening. So it's not if you're like a super rational person, you're going to say this is not a melee attack, but it still gives a very easy way to categorize a sequence into a way that you can sort of hang a little play on and better understand when you're looking at the code that this is happening sort of in melee range early in the attack sequence. Any other comments?
Is this a sort of simplification, or are there different kill something goals for different kinds of monsters, where you might not necessarily want to try melee before ranged, before items, and so on and so forth?
Yeah, there's a lot of engineering cruft that I've cropped out of these slides to try to just expose the core behavior. I find, like, for instance, Brett was talking about archers that get out of the way, right? And so what happens is that there are actually a bunch of events that fire in between these things that allowed me to more finely grained control over the system. So for instance, I have a component that's called shoot and scoot. And so what happens is that if a ranged attack succeeds, it will fire a ranged attack success message. The scoot and shoot component will watch for that and say, oh, I've successfully fired something. Let me push a run away for 3 turns goal onto the stack. And so you get these little archers that will shoot, got a successful range attack, and then will back away from you. And as long as you have enough hooks for those things to behave right, you can actually continue to use this very simple templated system and get a very wide range of behaviors out of your guys with just additional components that, again, are scale perfectly linearly. I can have 100 of these tiny little components, like cave spiders have components that make them like to scuttle off towards webs when they're bored, right? So you can hook into these events and have a wide range of behaviors with a linearly scaling amount of complexity. Any other questions?
Toward the beginning, you had the player moves to the right, and then the player put the wall down.
Yep.
And then you canceled the batch of the 3 moves, which was kind of like half the stack. And I'm wondering, do you have like stacks of stacks? Like, how did?
Right. So let's go back. So the question is, I canceled off a bunch of moves, and it might have seemed arbitrary. And I glossed quickly over it, but if you look at the goal implementation, you'll see that there's actually an original intent goal. So when something gets pushed onto the stack from a goal, it says, I'm the intent. And so what happened when these guys got pushed off is the red arrows indicate the intent relationship. So these move easts were pushed onto the stack from an approach the player. So that goal is their intent. So when a goal fails, it doesn't fail all the way back to being bored. It fails back only so far as the goal who created them, which was their intent. And it can decide whether it wants to fail or whether it wants to replan the attack. It's up to that internal goal.
So basically, cancels all of its siblings as it goes.
Yeah, exactly. So you can imagine it sort of as a nested stack. This is probably overcomplicated. I'm definitely not touting this as the end-all be-all of AI implementation. I'm only trying to share the solution that works for me in Caves of Cud. So, you know, at best, use it as a springboard for your own ideas.
Would you say that you use tweaks for the middle levels of these goal-achieving things? I imagine you have like small state machines.
Yeah, each of the goals is essentially a state machine, right? So a goal like the pilgrimage, right? The actual goal on a pilgrimage goal is a relatively complicated state machine, but it stays on the stack and it's able to manage its own states. If I was a better engineer at the time when I built the system, I might be more explicit about the fact that these are really state machines and more explicit about the fact that they're congruent in that way, but I'm not, and so some of them are better written than others, and the only real commonality they have is that they know when they're finished and they can take the next crank on the state machine progression. Any other questions? No? Okay, well, I'm done.
Alrighty, thank you very much. So we're gonna take a break for lunch. It's about 12:35, so hopefully 1:35. It might take me a little longer to get in touch with Adam Boyd, who's our next remote speaker. And then, yeah, so accent stickers are still around if you need one. Yet again, like yesterday, they are your ticket back up unless you feel like signing in with the front desk again. Enjoy. 1:35-ish. I'll let you know if there's more delays. I was just letting the stream know too. Like, there. Yeah.